Hello everyone, this is Lecture 10 of ComSci 142, Single Source Shortest Paths. In this video, we will discuss single source shortest paths for unweighted graphs and for directed acyclic graphs. And then later on in part 2, we will discuss two SSSP algorithms, which are Dijkstra's algorithm and Bellman-Ford algorithm. So let's start with the shortest path problem. As an input, you will be given an edge-weighted graph G and two vertices start and end. So your graph will have weights associated with each edge, and your goal would be to find the shortest path from the start vertex to the end vertex. Now, what do we mean by the shortest path? Now, from start to end, there could be multiple paths possible, right? So you could pass by different paths, but you want to find the path who has the whose sum of edge weights is at minimum. So let's say path 1 has a total edge weight of, let's say, 14, and then one has only 10, and then the other one only has 7. So you would pick, of course, the one with minimum total edge weight. Okay, so that is the shortest path. So some applications of shortest path would of course be on maps, like the Google Maps, trying to find the shortest path from point A to point B. And then you could also apply it to the friendship graph, like how many degrees of separation are there between you and a certain person. And of course there are a lot more other applications. Okay, but basically shortest path or path finding is another fundamental graph operation. Okay, so for our edge weights, they usually denote distance between the two nodes, but it's not limited to that. Okay, it's not limited to distance. It could also mean travel time or cost of traveling from A to B, or a certain penalty. Okay, so in general, it's just a quantity or a value that accumulates linearly. So you could add them up so that you could get the total of the total path weight, and then you're trying to find the minimum. Okay, so you accumulate it linearly, and your goal again is to minimize the sum of edge weights. Okay, so no matter what the interpretation of the edge weights are, it could be distance, travel time, cost, or penalty, your goal is to always minimize that sum. Okay, now there are 4 different flavors, or 4 different types of shortest path problems. And in this video, we will focus on the single source shortest path, or SSSP. But we'll also mention the 3 other types of shortest path problems. So for single source shortest path, or SSSP, we are given a graph as an input and a source vertex S. So the source vertex is where you will start your paths, and your goal is to find the shortest path from the source vertex S to every other vertex in the graph. Okay, so from one source to all other vertices, what would be the shortest path? The other type of shortest path problem is called single destination shortest path, or SDSP. This time, you're given a graph and a destination vertex. So it's not a source vertex anymore. It would be a destination vertex. So what would be your end point? Okay, your goal, or your destination, basically. So you're trying to find the shortest path from all other vertices going to D, with D as the destination. Okay, so it's different from single source, because from single source you start at S. In single destination, you end at D. Okay, but you compute this for all other vertices. Next is the single pair shortest path, or SPSP. And in here, you're only given a graph and a vertex pair X and Y. And your goal is to just find the shortest path from X to Y. So you're not trying to find all pairs either from S or going to D, but you're only finding the shortest path for one pair of vertices. Okay? And then finally, the last type is called all pairs shortest path, or APSP, wherein you're only given a graph G, and you're supposed to find the shortest path from each vertex x to each vertex y. So basically, all pairs of vertices. Okay, so what would be the shortest path from this vertex to all other vertices, and then you do that for all vertices. Okay, so for APSP, we will discuss this in the next video. Okay, because there are some other algorithms that would solve this one. Okay, but the reason why we'll focus on SSSP is because we can actually solve the 3 other problems just by using an SSSP algorithm. So how will we do that? So let's say we were doing a single destination shortest path problem. So we're an SDSP, but we only have an SSSP algorithm. So what we will do is, since we're trying to find the shortest path from each vertex to the destination vertex, what we will do is we will try to compute the reverse graph, right? So remember, the reverse graph is just the graph with all the edges directions reversed, right? So you'll reverse all directions and then find the SSSP on that. So this is possible because on the reverse graph, the source vertex would be the actual destination vertex of your original problem because you reversed the direction. Okay, so it would still be the same. Okay, so yeah. And then for single pair shortest path, if you were looking for the shortest path from vertex x to y, then you could just find the SSSP with the source being x. So starting from x and then find all pairs, but then you'll just get whatever is the shortest path for y. However, so far, there is no known SPSP algorithm that runs asymptotically faster than the best SSSP algorithm in the worst case. So, for now, there is still no algorithm that exists that would run faster than SSSP if you're just trying to find SPSP as in general, right? So asymptotically. So there could be cases wherein an SPSP algorithm will run faster, but that is only for some cases. It's not in the general sense. Okay, so yeah, you can use SSSP starting with X to find all pairs and then just isolate whatever is the shortest path from X to Y. So of course you're doing more work, but for now that is the best that you can do. Okay, you can't do better than it so far. And then finally, for all pairs shortest path, so you want to find the shortest path from each vertex X to each vertex Y. So what will you do? So you can run the SSSP algorithm n times, one for each vertex as the source. So let's say that you have 4 vertices, so you can run it with A as the source, with B as the source, C as the source, and then D as the source. And since SSSP is trying to find the shortest path from the source vertex to all other vertices, then you would have the all pair shortest path if you run SSSP n times, one for each vertex. Okay. However, there are better algorithms that exist instead of doing this. So we will discuss this in the next video. Okay. So let's see an example of an SSSP problem. So from S to T, what would be the shortest path? The shortest path would be would cost 3 because it would take this one, right? S to T. From S to Y, it would cost 5, the shortest path. Okay, maybe we can change the color. Okay, so maybe we can make this 3 and then this one is 5 because the shortest path would be either from S to Y, or you could take S2 and then ST TY. That's also cost 5, right? Going to X would cost 9, right? So either STX, which is 9, or SYX, which is also 9. And then finally here, this would cost how much? 11. Right? So this would cost 11 because either you pass through S, Y, Z, so that's 5 plus 6, 11, or it could also be S, T, X, so that's 9, plus 2, that's also 11, so Z. So the shortest path costs would be 3, 9, 11, and 5 if S was our source vertex. From S to S, it would cost 0, right? So that would be our shortest path. Yeah, so we have 3, 9, 5, 11, and 0. So that would be your single source shortest path solution. Okay, now let's try to think about this. Can a shortest path contain a cycle? If there is a cycle in the path, is it possible that that path is the shortest path? Well, no, it can't be. Because if you remove this cycle, the path still has the same source and destination but with a lower path weight because you removed that cycle. So for example, if we do, or so let's say we have a path A, B, C, and then going back to B, and then going to D. So let's say this is the path that we have. So A to B, B to C, C to B, and then back to D. Now there is a cycle here with B to C, right? And this would just add more weight. Like let's say this is weight 1, 2, 4, and then 1, or maybe even 4. So with the cycle, the total path cost would be 1 plus 2, 3 plus 8. That would be 11. But there is a better path that is still taking you from A to D, which is more straightforward. That would be removing the cycle. That would be just from A to B and then from B to D, right? So that would be 1 plus 4. So it's only cost 5. So it has a lower path weight when you remove this cycle. Okay? So shortest paths cannot contain cycles. Okay? However, in some graphs, there could be negative weight edges. So edges can sometimes be negative weights because, for example, if you're modeling energy transfer graph, like is energy gained or energy lost, something like that, right? So if energy is gained, that would be positive. If energy is lost, it would be negative. Or if you are modeling exothermic and endothermic reactions in chemistry, that would also be either positive or negative, right? So sometimes our edge weights could be negative. Now, if edge weights could be negative, then negative weight cycles could exist. So one example of a negative weight cycle could be like this. Now, why is this problematic? Because if this is a cycle, from U to V, it's negative 3. From V to U, it's negative 5. So that's a total of negative 8. And then if you take U to V again, it would be minus 3 again. So negative 11, and then minus 5, negative 16, negative 19, negative 24, negative 27, and so on. So if you take the cycle more times, your path cost will become lower and lower because it's a negative weight cycle, right? So this is a total net cost. One cycle costs negative 8. So each time you cycle, you are actually subtracting minus 8, or you're subtracting 8, right? So each time you take a cycle, you are reducing the path cost. So this is problematic because this will be difficult for you to find the shortest path. In fact, you cannot find the shortest path if there are negative weight cycles. Okay, So the shortest path cannot have negative weight cycles because you can just take the cycle as many times as you want until it reaches negative infinity, right? So you can traverse the negative cycle infinitely to reduce the path distance such that you can reach negative infinity as your minimum distance for the path. Okay, so we cannot do negative weight cycles. How about zero weight cycles? So examples of zero weight cycles would be this one, -3 and then +3. So the total net of this is 0. And then the same with this one, -3 minus 2, so that's -5, then +5, so that's also 0. So how about zero weight cycles? Can they exist in our shortest path? Well, yes, because the total contribution to the path is 0. So if you remove that zero weight cycle, it's still the same weight. But to keep things simple, let's try not to add zero weight cycles, because anyway, if you remove that one, it's still the same path weight, and then you're just adding more nodes to the path. So to keep our path simple and short, then we will also try to avoid zero weight cycles, even though technically they could exist in our shortest path. Okay? Now, for the shortest path algorithms, in part 1, we will discuss shortest path algorithms for unweighted graphs and for directed acyclic graphs, or DAGs. And then in part 2, we will discuss Dijkstra's algorithm for graphs with non-negative weights, and then the Bellman-Ford algorithm that will solve the shortest path problem for general situations, general graphs. Okay, so for now, we'll focus on these two first. Okay, now the brute force approach for finding the single source shortest path would be quite straightforward. So you'll just enumerate all acyclic paths, because we mentioned that paths with cycles cannot be shortest path, right? So enumerate all acyclic paths, and then for each path, you'll try to sum up the distances along the edges, and you just return the path with minimum total distance. So it seems straightforward. However, there's just way too many paths to consider. So of course, we won't even bother with the brute force approach. Now, one thing to notice, one thing that you'll notice also in shortest path is that it follows the optimal substructure. Now remember optimal substructure from dynamic programming and greedy algorithms. So the shortest path between two vertices contains other shortest paths within it. Now what does this mean? So let's say that you were taking the shortest path from x to y, and that shortest path also contains, let's say, the shortest path from x to z and z to y. So for example, if you were taking the shortest path from x going to y, and then somewhere along the road it passes through z. So this shortest path here will contain also the shortest path from x to z and z to y. Because otherwise, if this part here is not the shortest path, if there was a better path going from x to z, then that would have been the path that you would take to get the shortest path from x to y, right? So for this to be optimal, the subparts also have to be optimal. Okay, so because shortest path follows the optimal substructure property, then we can use dynamic programming and greedy algorithms later on. So we'll see both of them later. Okay, so let's start with unweighted graphs. So let's say that your given graph only has nodes and edges, and it doesn't have any weights. So how will you solve the single source shortest path for unweighted graphs? So for this example, so let's say that we start from S. Is this visible? It's kind of not. Maybe I will try blue. But this one. Oh. Okay, that's better. So if we do blue, Okay, so the shortest path starting from S, so if this is our source, then the shortest path would be 0, right? Because you're already at S itself. From S to T, it only takes one traversal because you have S to T, so that's 1. Same for S to W. This is also 1, right? Cost of 1. And then from S to U, it would cost 2 jumps, right? From so S, T, T, U. And then from S to V, it would also be 2 jumps because that would be either STV or SWV. So that is now your shortest path for this unweighted graph. So 0, 1, 1, and then 2, 2. Okay, so pretty straightforward, right? So formally, as an input, we will get an unweighted or equal weighted graph G and a source vertex S. So we also say that this is equal weighted because you can think of all the edges having cost of 1. Okay, so equal weighted siya or uniformly weighted. And you're trying to find the shortest path of V for each vertex V, and that is the fewest number of edges on the path from the source S to that vertex V. Okay, so you'll try to do this for all possible vertices. Now, there is actually an existing algorithm that we can use for this. So try to think about which graph algorithms we've already discussed so far, and which among those graph algorithms can we use to solve SSSP in unweighted graphs. So I'll give you 5 seconds to think about which algorithm that could be. Okay, so try to think first, and then let's see. Okay, so we can actually use a modified version of the breadth first search or BFS, okay, to solve SSSP in unweighted graphs. So how will that work? Okay, so first, what we will do is we will initialize the shortest path of each vertex to infinity. That means that for now, they are unreachable yet. So the shortest path from the source to that vertex is infinity, meaning I haven't reached you yet. Okay, then we will also initialize the shortest path going to the source to be 0 because you're already at the source, so you've already arrived at that vertex, right? And then each time we discover a neighbor in the BFS, right? So remember that in BFS we're exploring the neighbors in a per layer fashion. So every time we discover a neighbor, we will update its shortest path, okay, of the neighbor. And then the shortest path of the neighbor will be equal to the shortest path of the current node, the neighbor node, and then plus 1. Okay, because you are traversing the edge basically. So you're adding the plus 1 for that edge. And then basically, after everything has been solved, the node's shortest path length is equal to the layer number that it has. Okay, so which layer was it discovered, and that would be its shortest path length as well. Okay, so putting all of that together to look like this. So this part here is just initializing the shortest path of each vertex, so shortest path length. So initially, all vertices will have infinite shortest path, and then the previous, which would be used for the actual shortest path, like the backtrace, would be set to null. Okay, and then the source would be initialized to 0. And then this part here is just your basic BFS, right? So we're using a queue, we're keeping track of the explored nodes, and then we'll dequeue some node, and then for each neighbor, if that neighbor is explored, we'll skip it, otherwise we'll in-queue. And then we'll also mark that neighbor as explored. And each time we do this, we will update the neighbor's shortest path as the previous node's shortest path plus 1. And then we'll also update the previous to that current node, okay, so that we can do the backtrace later on. So it's pretty straightforward. We'll still just use BFS, right? So it will have the same running time and memory as your normal BFS. Okay, so we still visit the nodes once and visit the edges once, so this will still run in O of m plus n. Okay, so m plus n running time, and then O of n memory for the queue that we're using for BFS, right? Because at most the queue can hold at most n items, 1 for each vertex. Okay, so let's see this in an example. let's say we're given this graph. If we run BFS, so before we run BFS, we've initialized the SP of all the vertices to infinity, and then the source would be set at 0. Okay, and then the previous would be null. So currently in our BFS queue, we only have S. So we will dequeue that one and then look at its neighbors. So for the neighbors, it has T and W, and then after that we will dequeue T. And then when we dequeued T, when we enqueued T and W, we updated their shortest path and previous. So how did we update this? So this is, the previous one is S, right? So it has shortest path of 0, and then the neighbor would be +1, so T now has 1, and W also has 1. And then we updated their previous to the previous neighbor, which was S. Okay? So after that, we will dequeue T, and then the neighbors U and V were added to the queue here. And then when we added them, we will also update U and V's shortest path. So U will become 2, same with V. Because T already has a shortest path length of 1, so you add 1 to that, it becomes 2 for U and V. And then their previous becomes T, because that was the previous node that we encountered. And then for W, it's already processed, but yeah, we already processed this one, and then there are no more unexplored nodes, right? So we've already explored this one, so no more changes. And then for U, also no more changes. V, no more changes. So we are actually done now. Okay, so for S, the shortest path is 0. For T, shortest path is 1. Same with W, shortest path of 1. And then for U and V, shortest path of 2. Right? Now, how did we get the actual path? So we'll just follow the previous nodes. So starting from T, and then previous is S. So T, going back, then S, and then S's previous is null, so we'll stop. So we'll do that in reverse order. And then for U, for example, so you start with U, previous of T, then previous of T is S. So we have this one. Okay? And then for V, same thing. V, previous T, and then previous of T is S here. So you have STV in reverse. And then finally for W, W's previous is S, and then S previous is null, so you only have SW, or this path here. Okay? So you keep the previous backtrace so that you can recreate the actual shortest path, because for the BFS, we're only computing the shortest path length, right? Okay, so let's see one more example. But this time, what if it's a directed graph? Okay, if it's a directed graph, we'll do the same thing, but we'll just follow the direction. So from S, we will update its neighbors T and W, so they will be updated to 1, right? And then after that, T is next in the queue, so this will be dequeued, but it only has one neighbor now, which is V. Okay, because this one is in the opposite direction, so we'll just follow the direction. So T to V, this will become 2, right? Because 1 plus 1 is equal to 2. After that, the next in the queue is W, and then W's neighbor is only T, but that has already been explored, so we'll just skip it. So it still stays the same. And then V is next. Its neighbor is U, so we can update this to become 3, right? And then after that, it's processed. Then U doesn't have any unexplored neighbor, so we'll stop there. And then use the previous backtrace again to compute the actual path. Okay, so the only thing that differed here is that this one is already 3 because we're following the direction of the directed graph. Okay, so yep, so that was in the previous example, and then let's see one more example for this one. Okay, so if we start at S, for BFS, it will discover 3 nodes in the next layer. That would be A, B, and D. So they will all be updated to shortest path length of 1. Right? After that, A will discover neighbor C. So it will be updated to 2. And then B doesn't have any new unexplored neighbor, so we'll just skip that. D has an unexplored neighbor E, so we'll update that to 2 also, right? And then for C and E, no more new unexplored neighbor, so we'll stop there. And then to compute the actual path, just follow the previous backtrace again. Okay, so yeah, that's it for shortest path in unweighted graphs. Okay, so pretty straightforward, right? Now, do you think, so since we used BFS, do you think we can use DFS for the same problem as the SSSP for unweighted graph? Do you think we can do that? So let's try. If we used DFS here, what would have happened? So for DFS, this would have been, so 0, this would be 1, then go as deep as possible, 2, 3, 4, and then 5. And that would be already wrong, right? Because this one doesn't have a length of 5, it has a shortest path length of just 1, right? So we cannot actually use the DFS to solve SSSP in unweighted graphs. We can only use BFS because the per layer approach of BFS makes it correct. But that is only for unweighted graphs, okay? So, yeah. Okay, now, before we move on to other SSSP algorithms, there are actually some generic ingredients for each SSSP algorithm. And we will see that here. So first is initializing SSSP values. So you're given a graph G and source vertex S. So we'll see what we'll do for this method in a while. And then we will also see something called relax AB. Okay, so we'll also see what that means later. And then the SP of V, or the shortest path of that vertex, is the shortest path length from the source to vertex V. So this is only the length, okay? So this is a numerical value. And then the previous of V is used for the backtrace that will be used to recreate the shortest path. So we've seen this in the previous algorithm, right? So SP of V is the path length itself, and then previous of V is used for the backtrace. Okay, so let's try to start with initialize SSSP. So basically what we'll just do here is just initialize the values for the shortest path length of each vertex and the previous of each vertex. So you'll initialize that value to be infinite for all vertices, or 0 if it's the source, and then the previous of everything is null. So we did this actually in the BFS na SSSP for unweighted graphs, right? So it would look something like this. Okay, so SP of V is infinity, previous of V is equal to null for all vertices, and then you'll just set the source vertex shortest path length to be 0, because anyway you've already arrived at the source vertex. Okay, so it will loop through all vertices, so it would take theta of n, right? Because you're doing this for all vertices. Now, next is something called the relax function. So what does relaxation mean? So if you relax an edge AB, you are actually testing if going through vertex A will improve the shortest path going to B. Okay, so if going through A will improve the shortest path to B, then we will update shortest path of B, okay, and also the previous of B. So how does that look like? So what does it mean when we say it improves? So we will relax or improve the shortest path to B if going through A decreases the shortest path length. Okay, so this is the function itself. If the current shortest path of B, path length of B, is greater than shortest path of A, and then going through the edge from A to B. Okay, if this one is bigger, then we can improve through A. So if that is the case, then we will update shortest path of B to be equal to this value, because this one is smaller, right? And then we'll also update the previous of B to be equal to A, because that would have been its backtrace already. Okay, so because you came from A to go to B if you pass through the edge AB. Okay, so if that doesn't make sense, maybe it would make sense if I show you some examples. Okay, so in here, let's say that the current shortest path length of u is 5, and then the current shortest path length of v is 9, and then the edge weight from u to v is 2. So if we try to relax this edge, we're trying to figure out, is 5 plus 2 better than having 9? Well, 5 plus 2 is 7, right? So if I come from u, from vertex u, and then I pass through this edge with weight or cost of 2, that would only cost you 7, right? And that would be better than the current shortest path length going to v, which is 9. So I would relax this one and make this 7 and make the previous of v equal to u. Okay? So you're just checking this value plus this edge weight. Is that better than the current destination's shortest path length? So is it smaller? If it is, then we'll update or we'll relax it. Okay? Now, another example. How about this one? 5 plus 2, is that better than 6? Well, it's not, so we will keep it as is. So we'll only update or relax it if the sum of the source plus the edge weight is better or smaller than the destination's shortest path length. Okay? So that is relaxation. So, our algorithms for SSSP actually differ in the order and the number of times that they will relax the edges. Like for example, later on we will see that Dijkstra's only relaxes the edges once, whereas Bellman-Ford relaxes edges multiple times. Okay, so how many times the edges are relaxed would be how the different algorithms differ. Okay, so okay, and then so far in the algorithms that we'll see, we will also only compute the shortest path length. Now, if you want to compute the actual shortest path itself, then we will try to keep track of something called the backtrace. So, similar to what we did in dynamic programming, backtrace, right? So, we start at a certain node, and then we follow the previous node until there are no more previous, and then we will reverse the path because we are starting at the last part, right, at the node itself. So we'll just reverse it because we're following the previous. Okay, so you're already familiar with this if you've seen the dynamic programming lecture. Okay, so let's now go through excuse me, our second shortest path problem, which is we will be using it for directed acyclic graphs or DAGs. Okay, so a directed acyclic graph, of course, is a directed graph, so the edges have the direction, and since it's acyclic, there will be no cycles, right? So remember also that from the previous lecture video, we said that DAGs could be topologically sorted, right? We could use DFS to topologically sort our DAG. So if it's topologically if it can be topologically sorted, then we can always compute the SSSP in DAGs, okay? Because there would be no negative weight cycles that exist, okay? Because it's acyclic in the first place. So you're not worried about negative weight cycles. So what we will do to get the shortest path in DAGs is first topologically sort the graph. Okay, so we'll follow the topological sorting, and then in such a way that if edge xy exists in the graph, x should appear before y. Okay, and then we will process the nodes in topological order. So starting from the leftmost going to the right. Okay, and then we will relax edges that leave the current node that we're processing, and then we'll just do that in that order. Okay, so it's pretty simple. So putting all of that together, first you initialize the SSSP values of shortest path length and previous, and then we will topologically sort the vertices of the graph, assuming that it's a DAG. Okay, and then for each vertex of A, for each vertex A taken in topological order, then we will take a look at each edge. Okay, so the neighbor of B would be the edge AB, and then we'll try to relax that edge AB. Okay, so that's it, and then you'll do that for all vertices, and then you'll return the shortest path length. So for the analysis, for topological sorting, remember that this runs in O of m plus n, right? Because this just uses DFS. And then for each vertex taken in topological order, so this is O of n, right? O of n because it's each vertex. And then we're looking at each neighbor of A. So all in all, we're also looking at each edge once, right? For everything. Because you're checking each neighbor of the vertex that you're currently looking at. So that would be m plus n, and then plus m, and then plus n. So all in all, the total would be m plus n still. Okay, so topological sort is m plus n. Initialize SSSP is O of n, just you're initializing for all vertices. You visit the nodes once, it's O of n. Visit edges once, it's O of m. And then relax is just constant time because you're just comparing and updating. Okay, so the total running time is still O of m plus n. Then for the memory, you're taking O of n running O of n memory because you're using a stack for the DFS for the topological sorting. Okay, so it's pretty straightforward. And let's see an example. Okay, let's say that our source vertex is S, and if we topologically sort this, it would be R, S, T, X, Y, Z, right? Because if you do that, then excuse me. So if it's R, S, T, X, Y, Z, so R can go to S and T, S can go to T and X, T can go to Y, X, and Z, Y, X, and Z, X can go to Y and Z, and then Y can go to Z. So you'll notice that all edges are going forward. So this is the correct topological ordering of this DAG. Okay, so let's see this example. So initially, all the shortest path lengths are initialized to infinity, right? And then the source, which is at S, would be initialized to 0. Now we follow this topological ordering, right? R, S, T, X, Y, Z. So we'll start at R. So at R, it has two edges, right? From going to S and going to T. Now, can we relax this edge? So infinity plus 5, is that better than 0? Well, infinity plus 5 is still infinity, so that's not better than 0. So we cannot relax this one. Same with R to T. So this would be infinity plus 3. Is that better than infinity? Well, it's more or less the same, so we also cannot relax it here. Now, the next node is S, according to the topological ordering. So we're now at S, and we'll process each edge. So S to T. So can we relax this one? 0 plus 2, is that better than infinity? Well, yes, it is. So we will update T's shortest path length to 2, and then the previous would be set to S because this is where we came from, right? And then the next edge is S to X with weight 6. Can we relax this one? Well, we can, because 0 plus 6 is better than infinity. So X becomes SP6 and then previous of S. Okay, after S, we will go to node T, and it has 3 edges, but we'll start with TX. So TX, 2 plus 7 is 9. Is that better than 6? Well, it's not, so we'll just keep 6 as is. How about T to Y? Okay, T to Y, we have 2 plus 4, it's 6. That's better than infinity, so we'll update Y to have 6 and then previous of t. Okay? And then finally, we have t to z, which is 2 plus 2. This is 4. It's better than infinity. So we'll also update z to become 4 and previous of t. Okay? After that, after t, we will process node x. Okay? So the edges going out from x would be x to y. X to y, this would be 6. The negative 1, is that better than 6? Well, it is because it becomes 5, right? So we'll update y. This will become 5, and then the previous would become x, right? And then next, we have x to z. So 7, 6 plus 1, is that better than 4? Well, it's not, so we'll just keep it as is. After x, we'll process y, and it only has one edge. So 5 plus negative 2, is that better than 4? Well, 5 minus 2 is 3, and that is indeed better than 4. So we can update z to become 3 and previous of y. Okay, right here. And then for z, since this is the sync vertex, there are no more edges. So we'll stop here and we are done. So our shortest path lengths are as follows. So from R to S, it's infinity because there are no edges going from S going to R. Okay, there is an edge from R to S, but no edges from S to R. So R is actually unreachable. Okay, unreachable. That's why it has a shortest path length of infinity. Okay, from S to S, well, it's just in the node itself, so shortest path length of 0. From S to T, it has path length of 2 when you follow, well, S to T, right? From S to X, that would be 6, going from S directly to X. S to Y would be 5, and that is if you follow this one, S to X, and then X to Y. Okay? And then from S to Z, you'd follow S, X, Y, so that's 5, and then minus 2 becomes 3. Okay? So again, how did we get these paths? We just followed the backtrace for previous, right? For example, here, you have T, previous S, then S, previous null, so that we have T, S, then null, so ST. Then for this one, X, S, null, so X, S, then null. Then for this one, Y, X, then X, S, so we have Y, X, S. And then for this one, Z, Y, Y, X, X, S, so they have Z, Y, X, S here in reverse order. So that is your directed acyclic graph using topological ordering, and then we'll relax each edge in that order. Okay, so that's it. Yeah, so if we topological sort it, it looks like this, and then the final answer is 0, 2, 6, 5, 3. Okay, so if you draw it in the topological ordering, it's even easier to visualize, right? So you start here and then you check each edge. So infinity plus 5, no. Infinity plus 3, no. Then 0 plus 2, so this becomes 2. And then 0 plus 6, so this becomes 6. And then from here, 2 plus 7, so it's still the same. 2 plus 4, so this becomes 6. 2 plus 2, so this becomes 4, and so on. Right? So you just go through each node in order of topological ordering, and then relax each edge going out from that node. Okay? So that's it for topological sorting, or sorry, for SSSP in DAGs. So that's it for part 1. So we discussed single source shortest path so far, and we've used it for unweighted graphs using BFS, and then for DAGs we just relaxed it in topological ordering, and then yeah, so we uncovered the single source shortest paths. So that's it for part 1, and then part 2 will follow shortly. Okay, so we are now in part 2 of our single source shortest paths lecture, and in part 2 we will be discussing two SSSP algorithms, which are Dijkstra's algorithm and Bellman-Ford algorithm. So this one is Dijkstra, this one is Bellman, and then this one is Ford. Okay, so just like in our previous graph algorithms, we saw generic algorithms for specific ones, right? Like we had generic graph search, and BFS and DFS followed that generic algorithms pattern. Okay, they just differed on what type of data structure was used for the fringe, whether it was a queue or a stack, right? And then the generic MST algorithm was also followed as a pattern by prims and Kruskal's. They just differed on the order, or yeah, the order of edges, or which edges should be considered at each iteration, right? But more or less they follow the same generic algorithm steps. Okay, so in the same way, SSSP also has a generic algorithm. Okay, so this is the generic SSSP algorithm. So you're given a graph G and a source vertex S. So the first thing that you'll do is initialize SSSP. So we will initialize the SP values and the previous values. So SP would be initialized to infinity, and then previous would be initialized to null, but then the SP of the source vertex would be set to 0, right? And then we'll put S in something called the bag. So it could be any data structure later on. Okay, and then while the bag is not empty, so you take the vertex, some vertex A from the bag. So whether it would be a queue or a priority queue, it's not specified because this is generic. Okay, so just imagine that you have like a container, and then you'll take some vertex A out of it, and then for all edges from A going to some neighbor B, then we will try to relax that edge if it is tense. Okay, meaning you can improve that the vertex B's shortest path length. Okay, so we'll relax A, B, and then put the neighbor B in the bag as well, and then we'll continue this until the bag is already empty. Okay, and then after that, we've already found our shortest path length. Okay, so as I mentioned, the underspecified part here is how do we take items from the bag. Okay, how do we take vertices? Okay, so there will be different data structures for the bag for different SSSP algorithms. Okay, so some could be a first in first out queue, others could be a priority queue, and so on. Now, we've already seen two SSSP algorithms, right? So why do we need another SSSP algorithm? Well, it's because the first one that we discussed, the BFS one, was only for unweighted graphs. And, well, most of the graphs that we'll encounter here would be weighted. That's why we want to find the shortest path, right? Because there are weights associated with each edge. So most of them would be weighted, so we cannot use the BFS. And the second one that we discussed was only applicable for DAGs, or directed acyclic graphs. But in general, not all graphs are DAGs, and most of them will contain some form of a cycle, right? So we can't use that algorithm also for general graphs. Okay, so let's say for example for this one, how would we solve the SSSP here? So for this one, okay, let's see. Okay, so if our source vertex is S, then this would have 0, right? S to A would have shortest path of 1, if you take this one, right? S to B would be, well, 2, if you take this path. S to C would be 4, if you take SAC, right? That would be 4. S to D would also be 4 if you take SBD. And then finally, S to E would be 8, right? So it's 8 because it would you can take the path SACE and then that would be total of 8. Now if you took SBDE, that would be a total path weight of 9, because you have 2 plus 2 here, 4, then plus 5, which is 9. So that would be worse than having the upper path, which only takes 8. Okay, so that would be their so what was that again? Yeah, 0, 1, 2, 4, 4, 8, right? 0, 1, 2, 4, 4, and then 8. This would have been the correct SSSP algorithm, SSSP solution. But what if we used BFS on this graph? What would have been the answer? If we used BFS, okay, I'll use red for the BFS. So if we used BFS, this would have been 0 as well. And then it will discover the first layers, A, D, and B. So this would be 1, 1, and 1. And then for C and E, C would be discovered on the next layer. So this would be 2. And then E would also be discovered on the next layer, care of D. Right? So this would also be 2. So you'll notice that there are a lot of wrong answers, right? So we only had 2 correct ones, so 0, 0, and then the 1, 1. But the rest are already wrong. So this one is 1 and 2. This is 1 and 4. This is 4 and 2. This is 2 and 8. So a lot of the answers for our shortest path would be wrong if we used BFS on a weighted graph. Okay? So, okay. So, there's a lot of difference, right? So, we cannot use BFS if it is a weighted graph. But how about if we do like a clever transformation to make the weighted graph become unweighted? So maybe what we could do after that, if we can transform the weighted graph to an unweighted graph, then we can use BFS to solve our problem. So what we will do is, we will try, since each edge is weighted, right? So each edge has weight x. So we'll replace each edge with weight x with x unweighted edges. So what does this mean? So it would look something like this. If the edge from A to B has a weight of 3, instead of just one edge, we would replace it with 3 intermediate edges. So 1, 2, and then 3. And then we'll add more nodes in between. Okay? So these nodes are unnamed because we don't care about their the shortest paths going to them. We just care about A going to B. And then after this, since this is already unweighted, right? But this is still equivalent because there's still 1, 2, 3 jumps going to B. Okay? So if we do that, then we can use BFS. Right? Now the problem is, this expands the graph too much. Right? Because imagine if you had an edge with weight 1000. Then you would have to add like 999 more vertices to the graph, and then you would have to add 1000 edges just for one edge, right? So it would be too much. Okay, so if we do this transformation, then we can use a linear time algorithm, which is the BFS, but on a much bigger graph. Okay, so the the performance gains that we had when we used BFS would be offset because we are doing it on a much bigger graph. Okay, so what would have been better is if we used an algorithm that would be close to linear time. So it's not exactly linear, but it's close to it. But you're doing it on the original na small graph. Okay, you're not expanding it too much. Okay, so although we could do that transformation, right? So going back here, if our graph is something like this. Okay, so let's see. Maybe if we had a graph that, so I'll just do a simple graph with 3 vertices, so A, B, and C. So this one will be 3, this one will be 2, then this one will be maybe just 1. Okay, so to transform this would become A, B, and then 1, 2, 3. So 1, 2, 3. And then for C, it becomes 2. So there's 2 edges here. 1, 2, and then 1 lang. So you can transform it like this. And then for the BFS, it will run properly. But then, and then you will get the correct answer. But this is because we had small weights here. Now, if this was like 1,000, then there would be a lot of edges here. So it's not really efficient when you have big edge weights. Okay, so again, it would have been better if we chose a algorithm that's not linear but close to it, linear time, and then we're running it on the original small graph. Okay, so yeah, so the first algorithm that we will discuss in part 2 is the Dijkstra's algorithm, which was created by Dijkstra in 1956. Okay, so as the input, we will still get a weighted graph G and source vertex S. And the assumption for Dijkstra's algorithm is that each edge has a non-negative weights. So for the Dijkstra's algorithm to work, no weights should be negative. Okay, so it could be 0 or positive, but not negative. Okay, otherwise it will not work. Okay, so assuming that this assumption is true, our output would be the shortest path length of V, which is for all vertices V. SP of V is the length of the shortest path from the source vertex S to all vertices V. Okay, so that's our goal, our output. Now, the graph could be either directed or undirected. It doesn't matter. But take note here that this is already weighted. Okay? And the graph doesn't have to be a DAG. It could be any general graph. There could be cycles. As long as it only has one assumption. Okay? As long as it doesn't have any negative weights, then it should work well. Okay? So, Dijkstra also has another assumption. It assumes that there is a path from the source vertex S to every other vertex. That means that all vertices are reachable from the source. Because otherwise, then the path length would be infinity. Or it means that it's unreachable. Okay? So, if there is no path that exists from the source to that vertex, then the path length would just be infinity. Okay? That means that you cannot reach that vertex from the source vertex S. Okay? So, how does Dijkstra's algorithm work? First, we will still use the initialized SSSP. Okay, so we'll set the SPV of each vertex so to infinity, and then previous of V to null. Okay, and then we will start with the source vertex as being explored. So we will keep track of the nodes that we've already explored, and at the start we will explore the source vertex S. And then at each iteration, we will consider edges AB, okay, where A is already explored and B is not yet explored. Okay, so how will that look like? Okay, so let's see an example. So let's say that this is our graph, and let's say that our source vertex is S. Okay, so at the start, S is already explored, so we're coloring it with gray. Okay, so from because S is explored, which edges should we consider in this iteration? It would be the edges ST and SY. And why are those the candidate edges? Because ST has the source or the first endpoint as already explored, and then the destination is not yet explored. And then the same with SY, right? This part is explored, the destination is not yet explored. Okay, so those are the edges that we'll consider. Okay, A is explored, B is not yet explored. And then after that, out of those edges, we will select the edge that minimizes this equation. So shortest path of A plus the weight of the edge AB. Okay, so how will that look like? So going back to our example, so for ST, that would be 0 plus 10, because this is the shortest path currently of the source vertex, so that's 0, and then plus the weight of the edge, which is 10. So that is for ST, so that is 10. And then for SY, the same thing, 0 plus 5, so that would be SY's score would be 5. So we'll choose the minimum, and the minimum is, well, 5. Okay? So that is how we will do, or how we will select each edge at each iteration. So this is actually a greedy algorithm. Okay? And the reason why this is greedy is because we're trying to find the edge that minimizes this value. So you're trying to find the best possible path, because it minimizes the shortest path from the source, and then the weight of the edge that you'll pass through. Okay, so the one with minimum total value of this equation, that would be the one that we'll choose. Okay, so it's greedy. And then after that, we'll add that neighbor B to the explored, and we will set we will update if we need to relax it. We will update SP of B is equal to SP of A plus weight of AB, and then we will set the previous of B to A. Okay, so that is how Dijkstra's algorithm will work. So putting all of that together, it would look something like this. Okay, so we'll initialize SSSP, so we'll set the SP and prev, and then explored is initialized to S, and then while not all vertices are explored, the valid edges are those wherein edge AB where A is explored and B is not yet explored. Okay, and then the chosen edge at this iteration would be the valid edge that minimizes this equation, SPA plus weight of the edge AB, and then we'll relax that edge, right? So if it can improve the SP of B, we will improve it to this value. Okay, and then we will add B to explored, and then we'll do it again until every vertex has been explored already. Okay, just pretty straightforward, really. So as for the analysis, okay, for the analysis of the algorithm, okay, so this one will run in O of n, right? Because you're initializing the SSSP values of SP and prev, so you're doing this for all vertices. Okay, and then this while loop runs also in O of n, because you're doing this for all vertices, while not all vertices are explored. So that means that all vertices will have to be explored for this to n, right? So that would be O of n at most. And then at this part, you're choosing edges, right, that minimizes the SP of A plus weight AB, and then at the worst case, you'll have to look at all edges, so this would take O of m, and then the relaxed part is only constant, right? So there is a nested loop, there is a loop here, and inside the loop you take O of m time, so this would be O of n plus O of n times O of m. So in total, the running time is still O of mn because of this one. So since we're multiplying, we are iterating O of n times, and at each iteration we could do at most O of m work because we are choosing a valid edge. Okay, that is minimum. Okay, so again, initialize SSSP is O of n. The while loop is O of n because you're trying to make all the vertices be explored. And then when you select the edge, it takes O of m, so the total running time is O of mn. And for the memory, it's O of n because we're keeping track of the explored nodes, right? So that would take at most n vertices, so that's why it's O of n ang memory. Okay? So we can also improve this using a heap data structure, specifically a min heap, because at each iteration, take note that we are selecting an edge that minimizes this value. So if we're picking the min each time, then the min heap data structure would be really efficient for that one. Okay, so it would improve the running time. This time it would be O of m log n instead of O of mn. Okay, so there would be O of m heap operations, and then it takes O of log n per operation when you extract the minimum. Okay, so you could improve Dijkstra's algorithm by choosing the appropriate data structure. Okay, so before we go back to the demo, let's solve this manually first. Okay, so yeah, maybe blue is okay. So initially, their values for shortest path would be 0. I don't think that's visible. Maybe if I used yellow or red. Maybe red. It's also not very good. Maybe yellow. Okay, so 0. Okay, yellow is better. This would be infinity, infinity, and infinity, right? So we'll start at S. So this one is already explored, so I'll mark it with an X here for explored. So the edges that we'll consider would be this one and this one, because those are the edges wherein the starting point is explored and then the end point is not yet explored. So which one is minimum? 0 plus 1 or 0 plus 4? So of course that would be 0 plus 1, which is 1. So then we could relax this one and this will become 1, right? So that's 0 plus 1, so becomes 1 here. After that, what would be the valid edges? So it would still be this one, SW. So this one will be already explored, right? SW or this one, VW or VT. It's also possible because those are the edges wherein one endpoint is already explored, the other endpoint is not yet explored. So which one is minimum here? Is it 0 plus 4, 1 plus 2, or 1 plus 6? The minimum is 1 plus 2. So W's shortest path length would be equal to 3. And that is from here, 1 plus 2. So it becomes 3. Okay? And this one will be explored as well. After that, this one won't be a valid edge anymore because both endpoints are now explored. And then same with this one. Okay? So this is not valid edge anymore. So VT is still a valid edge, and then we'll add WT here as well because this is explored and then T is not yet explored. So which one will win here? 3 plus 3 or 1 plus 6? So the winner, the min, would be equal to 6, right? So if we take the 3 here plus the 3, so that would be 6. Okay? So your shortest path lengths would be S is 0, V is 1, W is 3, and then T is equal to 6. Okay? So that is how Dijkstra's work. So let's see one more example, and I can, I guess, show the demo now. So let's reset this one. So this is the graph, and then initially we set the SP to 0 for the source and then infinity for the rest. Okay, and the previous would be set to null. So the source vertex is the one that's explored first, and then the candidate edges would be ST and SY. The minimum would be SY because 0 plus 5 is lower than 0 plus 10. So will we relax 0 plus 5? So 0 plus 5, which is 5, is better than infinity, which is the current shortest path length of Y. So we will relax this one and update Y to 5. here, and then the previous is set to S. Okay? After that, we have a new set of candidate edges. Now we have more. We have 4, right? So we have ST, YT, YX, and YZ. So again, the candidate edges are those with the source vertex being explored, and then the end or the destination vertex being unexplored for now. So which one would be the minimums? Is it 0 plus 10, 5 plus 3, 5 plus 9, or 5 plus 2? So the minimum is YZ with 5 plus 2. It's 7, right? So will we relax this one? So 7, is it better than infinity? Yes, it is. So we will relax this edge and make Z be equal to 7, and then previous with Y, which is here. After that, we have a new set of candidate edges. This one is still valid. This one is still valid. This one is still valid, but this one hasn't is not valid anymore, right? It's replaced with ZX. Then this time, what would be the minimum? The minimum would be YT with 8, right? So should we relax this one? Yes, we will. So T from infinity becomes 8, and then the previous is set to Y. After that, we have a new set of candidate edges. We now only have 3, right? So it's TX, YX, and ZX, because this time only X is unexplored. So the minimum out of the 3 is the 8 plus 1, which is 9, right? Because this is 14, this one is 13. So 9 is better than infinity, so we will relax this one. So update X to 9, and then previous as T. After that, then we are done, right? So we now have the shortest path lengths from source vertex S to every other vertex in the graph. And then to form the actual path, we've already done this, right? So we'll just follow the previous. So from T, previous of Y, from Y, previous of S, and then S is null, so that's SYT. And for X, the same thing. So X, previous of T, and then the same thing. So it's still T, X, T, Y, S, and then reverse it, right? So for Y, previous of S, so SY. And then for Z, previous of Y, Y, previous of S. That's why you have SYZ as the path. Okay? So that is how Dijkstra's algorithm works. Okay? So this is the final answer. Okay. So, yeah. Now, if we have negative edge weights, however, we cannot use Dijkstra's algorithm anymore. So for this graph, we cannot use Dijkstra's because there is a negative edge weight here from T to W. Now, maybe we can also do some transformation of the graph. So if the graph has a negative edge weight, can we transform it to make the edge weights non-negative so that we can use Dijkstra's? Okay, maybe we can do that. So maybe what we could do is we could add a constant factor to the edges to make it non-negative, right? So we will reweight the graph to make the edges non-negative. So let's say, for example, in this simple graph, so we have a negative edge weight here from V to T, right, which is negative 5. Now, from S to T, the shortest path is SVT, right? Because this is 1 minus 5, it's negative 4. And then ST is only negative 2. So the shorter path is actually SVT with negative 4 na total length, right? But if we reweight this graph, what will happen is we will need to add a constant factor of 5. Okay? Why 5? Because if we add 5 here, this will become 6. If we add 5 here, this will become 0. If we add 5 here, this will become 3. And now, all 3 weights are already non-negative. Okay? So you will actually add the constant factor of the opposite or the absolute value of the smallest negative number. Okay, so the smallest negative number here is negative 5. So you add the absolute value of that one, or the opposite. So it's plus 5, so that it will at least become 0. Okay, now if that is our new reweighted graph, 6, 0, 3, right? If we add 5 to the 3 edge weights, this time, what would be the shortest path from S to T? So earlier, we said that the shortest path should have been SVT, right? But here, the shortest path is already ST with path length 3. So we changed the shortest path from the top path to the bottom path, which is already wrong, because even if you reweight the graph, you should not be able to change the actual shortest path, right? So the problem here is we actually added, although we added the constant value to all edges, we did not add the same amount of value to all paths, okay? Because to the top path, we added plus 10. To the bottom path, we only added plus 5. So why is that? Because in here, there's a plus 5 here, okay? So we added a plus 5 here, we added a plus 5 here, and then we added a plus 5 here. So for this path here, we actually added plus 10, and then here it's only plus 5. So there is an imbalance in the adding of constant factors to the paths. That's why the shortest path in the reweighted graph was changed to the bottom path, because we only added 5 here, and this one we added 10. So of course, this one would have shorter na. Okay? So this technique is not feasible for reweighting. Okay? So we cannot do this because it would not add an equal value among paths. Okay? So it doesn't preserve shortest paths. That's why we need another algorithm. Okay? So what if our graph has negative edge weights? We cannot use Dijkstra's anymore because Dijkstra's only works for non-negative edge weights. Okay? So that is why we will introduce another algorithm for SSSP, which is Bellman-Ford. Okay? Bellman-Ford is a general SSSP algorithm that works with any type of graph. So it could be a graph that is directed or undirected. It's weighted. The weights could be negative or positive. Okay, so it could solve some graph problems for SSSP that the Dijkstra's algorithm cannot solve, because Dijkstra's is limited to non-negative edge weights. This one can solve SSSP even with negative edges. Okay, and it will also detect negative cycles if one exists, because remember, we cannot have a shortest path if there are negative cycles, because if there's a negative cycle, then we'll just take that cycle as many times as we want to get the distance to be negative infinity, right? So now if our graph only contains non-negative edges, then of course Dijkstra's will be faster, because Dijkstra's is built to solve for non-negative edge weights, right? But if you apply Bellman-Ford on a graph with non-negative edges, it would still be efficient. It's just that Dijkstra's is slightly faster. Okay? So, yeah. So it's important to know whether the graph contains negative edges or not, because if it's all non-negative edges, then just use Dijkstra's because it would be faster. But if you're not sure whether it could have negative edges or not, then use Bellman-Ford so that you are sure that it will be solved correctly. Okay? So, for Bellman-Ford, we assume that there are no parallel edges, meaning multiple edges that connect two vertices. And if there are, then we will only keep the edge with minimum weight, because if we're trying to find the shortest path, even if there are multiple edges that connect two vertices, we'll only pick the edge with the minimum weight anyway, right? Like, for example, if from A to B there are two edges, like this one is 10, this one is only 3. Now, if you were to pass from A to B, which edge would you choose? Of course, you would choose the lower weight edge, right? So this edge will be used for the shortest paths and not this one. So just keep whichever edge has the minimum weight if there are indeed parallel edges. Okay? So, a short background on Bellman-Ford algorithm. It was discovered by Schimbel in 1955 and also by Richard Richard Bellman in 1958. Now, Bellman, when he created this one, used Lester Ford's relax procedure. So remember the relax procedure that we've been using for other SSSP algorithms? That was created by Lester Ford in 1956. And Bellman, in his algorithm, used this relax procedure. So, it's also worth noting that Richard Bellman is actually the father of dynamic programming, and Bellman-Ford algorithm is actually a dynamic programming algorithm, right? But what I'll show you today is a simplified version wherein we'll just iterate many times, but you can still think of it as dynamic programming. Okay, so yeah, it's called Bellman-Ford, but there was no collaboration between Bellman and Ford. Okay, it's just that Bellman used Ford's procedure, ang relax procedure, so that's why it's called Bellman-Ford. Okay, sometimes it's also called Bellman-Schimbel. Okay, so how does Bellman-Ford algorithm work? So the idea is we will use the relax procedure on the edges many times or multiple times. So by doing this multiple times, we will repeatedly decrease the the SPV value, so the shortest path length of the vertex V, until it achieves the actual shortest path length. Okay, so excuse me. Let's contrast this with Dijkstra's, which only relaxes the edges once. Okay, so Dijkstra's, when you've already explored that edge and then the other endpoint is not yet explored, then it's part of the consideration. But once both endpoints are already explored, then we won't consider. We will skip it already, right? So each edge would be relaxed only once at most. But here in Bellman-Ford, the edges would be relaxed multiple times. Okay, so that is their difference. So what we'll do is first we will set a fixed order of edges. So it's arbitrary. You can fix it as however you like, as long as it's the same order that you'll use per iteration. Okay, so it's a consistent order of edges, and then we will relax each edge in that order. And if at least one edge is relaxed in this iteration, then we will repeat, okay, for a maximum of n-1 rounds. So let's say that if you have 5 vertices, then you would do at most 4 rounds, because that would be 5 minus 1. Okay, so you can also stop early if there are no more edges that is relaxed in that previous round. But if there are still at least one edge that's being relaxed, then continue. Okay, so that's it. That's the idea for Bellman-Ford. Just repeatedly relax each edge in following a fixed order. Okay, until either you've reached n-1 iterations or no edges have been relaxed, so you can break early. Okay, so Bellman-Ford is pretty straightforward. You can initialize the SSSP first, and then for iteration from 1 to n-1, because again, we'll only do this for n-1 at most iterations. And then for each edge in the graph, following a certain order, we'll try to relax that edge. And if no edges have been relaxed in this round, then we'll break early. Okay, and then this part tries to detect a negative cycle. Okay, so for each edge AB, if the shortest path of B is greater than SP of A plus weight AB, then there is a negative cycle, because going to B is more than going from A and then passing through AB to go to B. Okay, so there is a better path if you stayed from A and then passed through AB. Okay, so it means that there is a negative cycle. Okay, so this part detects the negative cycle, and then if there are no negative cycles, then it will return the shortest path length. Okay, so for the analysis, okay, let's go back here of Bellman-Ford. Okay, so initialize SSSP will run in O of n, because this will initialize the values for each vertex. Then this one will also be O of n because you're doing it for 1 to n minus 1. So that's O of n. Then inside each iteration, you're checking each edge. So that would be O of m, right? And then finally, for the last part, you're also doing it for each edge. So this would be O of m. So in total, that would be O of n plus O of n iterations, and then per iteration you're doing O of m work, and then plus the O of m at the end. So this is still O of, the running time is still O of mn, because the biggest factor here is this one, n times m. Okay, so that's stated here. So initialized SSSP is O of n, outer for loop is O of n, inner for loop is O of m because you're going through each edge. And then to check the negative cycle, it's O of m. So in total, it's O of mn. Now for the memory, it's just constant because you're not using any extra memory for this one. Okay, so let's see an example of Bellman-Ford. So let's fix the order of the edges as follows. So it could have been any other order, but let's say that this is the order that we came up with. So if that is the order, so we'll go through it in this order, ang edges. So we'll start with Tx. Should we relax this one? Infinity plus 5. Is that better than infinity? Well, no. How about Ty? Will we relax this one? No. Tz, relax? No. Xt, relax? No. Yx, relax? No. Yz, no. Zx, no. Zs, no. How about St? Now for St, it's 0 plus 6, which is 6. Is that better than infinity? Yes, it is. So we will relax this one and update T to 6 now, and the previous is S. Okay? And then for Sy, we will also relax this one because 0 plus 7, which is 7, is better than infinity. So Y will be updated to 7 and previous of S. Okay? Now since there were two relaxations in this iteration, we will proceed. We'll continue. How about Tx this time? Can we relax it? Well, this time we can because T's value is no longer infinity. So 6 plus 5, which is 11, is better than infinity. So we will relax this one. So x becomes 11, previous of t. How about Ty? Is 14 better than 7? It's not. So we'll keep it as is. How about Tz? 6 minus 4, which is 2, is that better than infinity? Well, it is, right? So we will relax this one. So z will become 2 and previous of t. Okay? Xt. So x has 11 and then minus 2. So that's 9. Is that better than 6? It's not. So we'll keep it as is. Yx, 7 minus 3. Is that better than 11? It is. So we will update this to 4 ang x. So x becomes 4, previous of y. Okay? Yz, 7 plus 9, that's not better than 2, so we'll skip it. Zx, 2 plus 7 is not better than 4, so skip. Zs, 2 plus 2 is not better than 0, so skip. St stays the same. Sy also stays the same. So we're done with the second iteration, but we had some relaxations in the previous round, so we'll continue with iteration number 3. Tx, this time 6 plus 5, is that better than 4? It's not. Ty, 14, is that better than 7? No. Tx, 6 minus 4 is still 2, so it stays the same. 4 minus 2, is that better than 6? It is, right? So we'll update t to become 2 now. Okay, so t becomes 2, previous of x. Okay, now after that, yx, 7 minus 3, it's still 4. So keep it as is. YZ, no, skip. ZX, 9, not better than 4, so skip. ZS, skip. ST, skip. SY, skip. Same thing. But we had at least one relaxation, which is XT here. So we'll still continue to the next round, which is iteration number 4. And iteration number 4 is already the last round because we only have how many vertices? We have 5 vertices. So we will go from iteration 1 to iteration 4. So it's n is 5, so n minus 1 is 4. So this will be the last round already, regardless of whether there are relaxations or not. Okay, so for TX, can we still improve this one? 2 plus 5 is 7, not better than 4, so no. TY, 10 is not better than 7, so no. TZ, 2 minus 4, that is better than Z, which is 2 currently, so we will improve this one, negative 2. Okay, so it becomes negative 2, and then the previous is T. How about XT? 4 minus 2 is still 2, so skip. YX, 7 minus 3 is still 4, so no. YZ, no. ZX, no. Okay, because even if this one change, negative 2 plus 7 is 5, but that is not better than 4, right? And then ZS, how about this one? Negative 2 plus 2 is still 0, so the same, no. ST and SY, still no. So even though we had change here, this will already be the last iteration, okay? Because we're only going from iteration 1 to n minus 1. Now, even if we go for one more iteration, there will no longer be other what do you call this, updates, because for example from here you can even notice the node that we updated was Z, right? But for ZX and ZS it already had no relaxation, so there won't be any change in the next round anyway. So we are actually done now. Okay, so after getting the shortest path lengths of each vertex, and then using the previews, we can recreate their paths using backtrace. So let's try to look at each one for each vertex. So for S, of course, for S to S, that would be 0, so stays in S itself. From S to T is 2, and how will we get 2? So we will go from S to Y to X to T. So S to Y is 7, minus 3, that's 4, minus 2, 4 minus 2 is 2. That's why we get 2. Okay, so that is the shortest path, S, Y, X, T. Now for X, well, it's the same path here, S, Y, X. So maybe I'll use red, or this one, magenta, or whatever. S, Y, so 7 minus 3 is 4. So that's why we have 4 here for S, Y, X. And then, of course, just from S, Y, this would be 7, just from going from here to here. Okay? And then for Z, okay, maybe I'll use another one here. For Z, we have negative 2. How did we get negative 2? Okay, let me clear out the others. So we go from S to Y, so that's 7. 7, Y to X, so minus 3, that's 4. X to T, so that's how much? 4 minus 2 is 2. And then from T to Z, so we pass by negative 4. So 2 minus 4 is negative 2. That's why we have negative 2 as its shortest path. Okay? So S, Y, X, T, Z. That is the actual path for Z. Okay? So that's it for Bellman-Ford. So just fix the order of the edge, and then go through each edge in this order relax them if you can. And then if in that iteration there was at least one relaxation, then we would proceed to the next, and then maximum of n minus 1 iterations. Okay, so that's Bellman-Ford, and yeah, that is the SSSP values that we found out earlier. Now, if it was something like this is a negative cycle, right? So 3 and then minus 5. So let's try Bellman-Ford for this one. So that would be S, there is a edge ST and then TS. And then since there are only two vertices, so we will only do this for one iteration, right? So this is 0, this is infinity. So can we relax ST? So 0 plus 3 and infinity. So yes, so T will become, okay, so I'll make this blue. So from 0 and then infinity, this one will become 3, right? So we're done with ST. And then from TS, 3, negative 5, so that's negative 2. Will that improve 0? So yes, so this becomes negative 2. So now, our final values for S and T are, for S, it's negative 2, and then for T, it's 3, right? But if we go back to the algorithm, we need to check each edge and check if SP of B, which is the destination, is greater than SP of A plus weight of AB. Okay, so let's check. So in here, so let's check edge ST. For edge ST, negative 2 plus the edge weight here is 3. 3, is that less than SP of B, which is 3. So 3 minus 2 is 1, and it's less than 3, and because of this there is a negative cycle that is detected. Because remember that if there is one edge that has this one, right? So it was, the conditions were SP of B is greater than SP of A plus weight of AB, right? And if this is true, then there is a negative cycle, right? And that was true here because SP of B, which was the destination, is 3, right? So 3 was greater than SP of A, which was negative 2, plus the weight of the edge, which is 3. So 3 was greater than 3 minus 2, which is 1. And this is true, so there is a negative cycle. Okay, so we've also detected a negative cycle if it existed, because this is indeed a negative cycle, because this is 3 minus 5, so that's negative 2. So the net weight of the cycle is negative 2. So you can always take this cycle to subtract 2 each time. Okay, so it's a negative cycle. Okay, so that's it for SSSP. So to review, we discussed two algorithms in part 2, right? Dijkstra's algorithm and Bellman-Ford algorithm. So to review how they work, Dijkstra's is greedy. Okay, so it tries to select candidate edges wherein one endpoint, the source, is already explored, and then the other endpoint is not yet explored. And then out of those candidate edges, we will select the one that minimizes SP of A plus the weight of the edge AB. Okay, and then we will continue that until all vertices have been explored. Then for Bellman-Ford algorithm, which is a dynamic programming algorithm, how it works is we'll fix the order of the edges, and then after we do that, we will follow that order and relax each edge one at a time. And then after doing that, if at least one edge has been relaxed, we'll continue to the next iteration for a maximum of n-1 iterations. Okay, so pretty straightforward. So Dijkstra's only works when you have non-negative edge weights. Then Bellman-Ford can work for general graphs. So you could have non-negative edge weights or negative edge weights, doesn't matter. Bellman-Ford will solve it for you. Okay, so that's it for this video. If you have any questions, please don't hesitate to ask, and I will see you in the next video.